Hello everyone. Today we are going to look at the case study on cold shut and die casting. Okay, so this is Dr. Ilangovan, and then I am from professor in the Department of Aerospace Engineering from the SNSCT College of Technology. Let's get started. So what is die casting? It is a metal casting process, and it is used. High pressure is used, and then the molten metal is forced into a cavity here. Okay, and whatever is the shape of the cavity or the mold, the parts are formed accordingly. So a simple explanation goes like this: the molten metal goes into the cavity and gets formed as per the shape of the cavity. Well, but there are multiple errors that happen during the die casting process. There could be like gas porosities, then drags and soldering can happen, blisters can happen, then cracks developed, deformations happen sometimes, and then there are flow marks, which is not desirable. There's a cold flow where the metal gets the temperature of the metal gets comes down, and then there are turtle cracks and network cracks. But among this, today we are going to look at something called as a cold shut. The cold shut occurs when two relatively cold streams of molten metal from different gates meet and do not fuse together. That means one set of material comes out here, and then one material, one flow of material comes here. They both come and meet here. The front of the material is already cold because it was facing cold air, and then so it gets into this, and then both these metal together, when they join here, they develop a kind of a welding point or a crack here, and this is be a weakest point, which is not desirable. Okay, so cold shut should be avoided, and so let us look at how we can avoid cold shut in a particular case study. The case study that we are going to take over is for the Hero Motor Corporation, and then we found that there is a lot of rejection data, and the rejection data due to the cold shut is very high here. The porosity is also contributing, the shrinkage is contributing, slag is there, and so the whole thing is contributes to the uh, rejections. So let us attack one after the other, but then today we will concentrate only on the cold shut. Now, there are the methodology that is going to be used as the 7C tools, which has a check sheet, a fishbone diagram, or the Ishikawa diagram, or the histogram chart, the Pareto analysis, then the control chart, scatter diagram, and stratification. These are all the different tools which are being used for trying to eliminate the defects that happen in a thing, and then they try to pinpoint where the problem occurs, and then it tries to bring down the rejection rate. Okay, so first one, there is the brainstorming that has been done by using the concerned people. There will be the lab in charge, the quality manager, the furnace supervisor, the worker at the furnace, and the mold supervisor. All these people sit together, and then they try to do a brainstorming, and then they try to find out that there's a lower pouring temperature, low silicon and phosphorus, slow or intermittent pouring is there, slow ladder carrying, okay, or and the damage patterns. Now all these put together, if you put it into the hows and whys of the whole thing that is happening, okay, why the whole cold shut happens, there is we have a fishbone diagram or the Ishikawa diagram. Okay, the measurement happens in during the measurement. What are the problems? Measurement, temperature measurement could be wrong. The weight measurement of the alloying elements could go wrong. The materials, thin wall sections could be there. Improper alloy composition could be there, and heat transfer by the cold material there. There are personal problems which happen. Slow or intermittent pouring, slow lateral carrying has been pointed out, and then that we put it here. Environment could be one of the problem, but right now nobody has contributed any point towards the environment. Methods could be like low pouring temperature, and then the machines, the damage patterns are always there. Now all these put together, they point towards a cold shut. Now we'll have to eliminate this study after we eliminate this defects after we study through the entire we break down the points, and then we try to study in depth about it. Now, the trials were conducted on 120 castings into two levels on 30 kg capacity induction furnace. Trials are shown below in the table. The first two rows in the table represent the random readings taken. These are the random readings that have been taken. Okay, the first two one. Okay, the random readings have been taken in the, and then they went on for the trial 1, 2, 3, 4. Okay, they have taken the temperature, the percentage of phosphorus, then the silicon percentage of of silicon, then the silica, then sample size, how much were good and how much were bad, and how much had cold shut. Now this was collected as an experiment, and then the study went. Now the following are the histograms showing the effects of pouring, of temperature, percentage of silica, and the percentage of phosphorus on rejection, uh, and uh, and as per the results of the trials conducted, here the number of defects are shown here, the number of rejections based on the temperature are shown here, and there are a number of rejections based on the silica are also shown here. Okay, now these are being plotted only for the trials that have been taken. Now, there has been a discussion that happens as the defect sand porosity and shrinkage requires lower pouring temperature in the recommended range, and cold shut requires high pouring temperature. So the temperature range observed, which can be useful to reduce the cold shut, considered the other defects, is 1418 to 1000 14,320 degrees Celsius. Now, phosphorus percentage is recommended to be 0.12 to 0.2% uh, the as the phosphorus increases the flowability, and it is recommended that to keep the percentage level towards the upper limit as 0.0, 0.2. Okay, higher than this may cause the shrinkage porosity in the castings. The silicon percentage was also found to be was recommended to be 1.83 to 2%. About 2% mainly responsible for porosity in the casting, and lower percentage may reduce the flowability and causing cold shut. Okay, so this discussion has come out, and then they have studied these things, and then they try to eliminate the defects there. The entire study was published as a paper, and this is the reference that is being given. And here we see that the investigation and analysis of cold shut casting defects and defect reduction by using the quality control tools, and I acknowledge the authors for the same. Okay, so thank you very much, and then let's meet once again on a different case study. Thank you very much.